Welcome dear students. This time I am welcoming again the students who are following our lectures on this it is linear differential equation with constant coefficients. Linear differential equation with constant coefficients, lecture number 15. Well, in lecture number 14 what we did, we have actually done there linear differential, homogeneous linear differential equations with variable coefficients. Actually we could reduce that by a suitable substitution into linear differential equations with constant coefficients. By the substitution, what was the substitution there? If you remember, x is equal to e raised power z. Please go to lecture number 14 when you will come to this lecture number 15. Actually I have received on my WhatsApp account the messages from some students who are doing BTech in engineering, perhaps second or third sem. There they have mentioned this in the syllabus. It is mentioned that Legendre's linear differential equation is reducible to this constant coefficient. It is actually this part is there. It is linear differential equations with variable coefficients reducible to linear differential equations with constant coefficients. There are different types of this. One is that we did in our this lecture number 14, where we considered the homogeneous linear differential equation, which we could reduce to the linear differential equation with constant coefficients by a suitable substitution in lecture number 14. Now about this, it is Legendre's linear differential equation with variable coefficients, which can be reduced to the linear differential equation with constant coefficients. Then we come to the previous method of solution. Well, but some students who have in their syllabus general this Legendre's differential equation and Bessel's differential equation in power series solution, they should not get confused. There you have, I will write here that equation. That equation is this time 1 minus x square d2y by dx square. It is derivative of this comes out to minus 2x dy by dx plus n times n plus 1 equal to 0, where n is not equal to plus minus 1. This is also the Legendre's differential equation. It is solution comes in power series. Remember this. When we come to the power series, we have to deliver some lectures on the power series solution. In power series solution, we will be discussing this solution of this Legendre differential equation. This Legendre differential equation, it will come in power series solution, and from this differential equation we get some functions which are sometimes known as the spatial spatial type of functions, like you have the Legendre's polynomial function. You have the first kind, Legendre's polynomial equation, second kind, that will come there in power series solution. Those students who will have in syllabus power series solution, in power series solution it is mentioned Legendre's differential equation, it is mentioned there Bessel's differential equation, some have Rodkirch's differential equation, Chebyshev differential equation, and so on. But this is different from this, although it is also a Legendre differential equation here, it will be also second order, but it is different from this. You will not get confused by this. Here we have the solution of this in power series. Here you have general number involved, n into n plus 1. Now leave this. Let us come to we define first what is this Legendre's linear differential equation and how we reduce this Legendre's linear differential equation into our previous type, that is the linear differential equation with constant coefficients, and then I will give you the method of solution in between that. Let us define. We will define this in this way. Let us define this. This is the definition. We write a differential equation, in fact a linear differential equation of the form, it is of this form. Let us take here a plus bx raised to power n dny dxn, then plus a1 a plus bx n minus 1 dn minus 1y dx n minus 1 plus so on plus a n minus 1 a plus bx dy by dx plus a n y is equal to x. This is this differential equation where your I running from 1 to so on to n are constants. Please follow my definition, the definition that I am first giving you. These are constants, and capital X right side, capital X is some function of, it is some function of x. It is some function of x. Okay. Will be called, is called Legendre's linear differential equation. Order is nth order, but degree is 1. That is why it is called the Legendre's linear differential equation. Now we will learn here how to solve this. We solve this linear differential equation. You see how you just recognize it. You have here any linear factor here raised to n, and this n should coincide with the order of this. Order of this derivative is n, dny dxn. You see here you have a plus b x raised power n minus 1. Linear, again the same linear. It is power is n minus 1, and this should coincide. This should be same as the order of this derivative. Next you see last a plus last but one term, a plus bx. It is of first order. Dy by dx is of first order differential. Then plus a and y is equal to x. You can see this way. You can recognize in this way. Now I will give you the method of solution, how we solve such differential equation. Method of solution, I will rub it. I have given, this is the definition of this. Next we come to method of solution. You see how we go, it's method of solution. Method of solution is this. In order to reduce or convert or transform, whatever you use, in order to reduce equation number 1 into one with constant coefficients. Remember this, the unit we are doing starting from lecture number 1 to lecture number 14, including this 15. It is the how to solve the linear differential equations with constant coefficients. It is this. And in this case we have also included now the linear differential equations with variable coefficients which are reducible to linear differential equation with constant coefficients. The first of this type comes the homogeneous linear differential equation that you did in lecture number 14. Now I am also taking this one, Legendre's linear differential equation, how to solve it. Method of solution is we want to reduce it into one with constant coefficients. The suitable substitution is, we make here suitable substitution. Remember this substitution. If you remember, in case of homogeneous case, we put x is equal to what? E raised power z. X was there linear, powers of x were running there. First x raised power n, dny by dxn, then plus x raised power n minus 1, dn minus 1 dxn minus 1 there, and there we put x is equal to e raised power z. Here linear factor is your, we put a plus bx is equal to e raised power z. This is the suitable substitution for this. You will remember this substitution for this Legendre differential equation, how we reduce it to the corners. How it gets reduced? Let us see. Now when you put a plus bx is equal to e raised power z, this will imply z is equal to what? Log of a plus bx. How it is? When you apply log on both sides, what you did in previous case in lecture number 14, when you apply log on both sides, it is log of a plus bx is log of e raised power z. Z comes down, log is 1, so it is z is equal to e raised power log x. Now we have to work with this. We have to use it from start to the end. Remember this, z is equal to log of a plus x. When you put z is equal to log of a plus x, how my aim is to find out these terms, this term, so on, this term. Then I will use it in first. Then first it will reduce to the linear differential equation with constant coefficient. Let us see how we go. Well, I will use here, this will imply me here when z is log of a plus bx, if I differentiate this, what is this? dz by dx. क्या आएगा dz by dx? Differentiation of log 1 by the function. It is 1 by a plus bx. Then differentiation of power in the numerator, it is b. Therefore your dz by dx is nothing. It is b upon a plus bx. I will be using it in future course. Okay, let us now see. Let us see how we find out by chain rule. Now dy by dx, right? It is dy by dz into dz by dx. Chain rule I am using. This gives me dy by dz into, what is dz by dx? It is over this dz by dx. It is b by a plus bx. Therefore, I will name this here dy by dx. I am getting b by a plus bx into dy by dz. Let us name this equation second. Okay, so this second now gives equation second implies what? Equation number second. You see what does this imply? This gives a plus bx into dy by dx is equal to b times dy by dz. Okay, this I will write now a plus bx dy by dx is equal to b capital D. Name this equation number third. What is capital D stand for? As previous we did, capital D stands for d by dz. I am using here operator, symbolic operator, converting this into symbolic operator form. I am using d by dz as d, so this is my b dy. It is b dy. Remember this. It is b d by dz is d. It is b dy, where d is d by dz. Remember this. It is b times dy. Okay. Now I will remember this. Rob this. You can take the screenshot of this if you remember it. I need this one. I need this. I need this. I need also second one. Okay, let me rub it now. Now differentiate equation second with respect to x. Why I am doing this? I want to find out now d2y by dx square. Similarly, then d3y by dx cube. I will get at something symmetric result. Then I can extend this up to a plus bx raised power n dny dx. And you see how when I differentiate this equation second, look here, it is d2y dx square is equal to, it is derivative of b by a plus bx times dy by dz. It is with respect to x. Now I can go with this. I can go by chain rule here. You see how this gives me derivative of b by a plus bx with respect to x, derivative of first function, write second as it is, dy by dz, then plus b by a plus bx as it is, derivative of second function, it is d differential of dy by dz with respect to x. I am differentiating with respect to x. Now it is equal to, what is derivative of this? A plus bx. It is derivative of a plus bx in the numerator, that is b, but it is minus b times this differential of, you know, what is differential of 1 by a plus bx with respect to x? It is minus b by a plus bx whole square. अगर आप इसको ऊपर भी ले जाएंगे, उस हिसाब से भी करेंगे, तब भी आपको यही मिलेगा. हाँ, this is it is derivative. B is here multiple constant, take it out, derivative of 1 by a plus bx, I have written here, it is minus b by a plus bx square, minus b by a plus bx square. Then dy by dz as it is the second term I will write here, it may not get mixed up. This term is plus b by a plus bx. How I differentiate this? It is independent variable here z, here it is x, so I can use chain rule. How? I will write it derivative of dy by dz with respect to z, I need with respect to z, then dz by dx. याद रखने का ढंग यही है, आप कहते हैं ये और गया है, फिर दोबारा आएगा with respect to x. So we have used here chain rule. This is your d2y dx square is equal to, it is minus b square by a plus bx का square dy by dz, then plus b by a plus bx. This is your d2y dz square. What is d by dz? It is here. It is b by a plus bx. The value of b by a is dz by dx. Okay. Well, on simplification, what does this give us? It gives d2y dx square is equal to minus b square by a plus bx square dy by dz, then it is plus b square by a plus bx square d2y by dz square. Now multiply both sides by a plus bx square, both sides. This will be here a plus bx square d2y dx square is equal to minus b square dy by dz plus b square d2y by dz square. Now this gives me a plus bx square d2y dx square. I can write here, once take here b square common. When you take b square, d by dz is d, it is minus dy, because d by dz is d, it is dy, minus dy, b square is out, it is plus d square y. So that this is what now? It is b square, take d out, when you take d out, it will be d minus 1 into y. So this is your equation number 4th. Now you see you have got a plus bx dy by dx b dy. Here you have a plus bx square d2y by dx square, b square one factor increases, d into d minus 1 into y. You can write similarly. In previous case we did in lecture number 4. you can write here after this. Similarly, on similar lines, similarly we can have now a plus bx cube d3y dx cube will be according to this. Here when you have square here, it is b square, here it was b raised power 1, so naturally it will be here b cube. It is d, then d minus 1, one factor will get add, d minus 2 into y. This is your fifth equation, and so on to proceeding up to nth. When you proceed up to nth, what you get? You get a plus b x raised power n dny dxn will be equal to b raised power n d into d minus 1 d minus 2 d minus 3. Last it will be, you see when you write d, this factor, it is d into d minus 1, that's derivative is second, you can write it is d minus 2 plus 1. Here you can write last factor d minus 3, this 3 minus 3 plus 1. Here it is d minus n plus 1 into y. Using, this is sixth, using third, fourth, fifth dash sixth in first equation. When we use these values in equation number first, what we get, the given equation first is reduced into linear differential equation. When we use it there, what we get, the given equation number 1 is reduced to linear differential equation with constant coefficients, and can be solved by previous methods. What are your previous methods? Your previous methods go before lecture number 13. Whatever methods we have before lecture number 13, when you have the complement particular integral, how you find out particular integral, when it takes algebraic form, when it takes a trigonometric form, when it takes any other form, how you solve that. That is why I have written that we can solve it by the previous method. I hope you have understood it was this method of solution, how we solve the linear differential equation with this variable coefficients. But you see, in case of variable coefficients, there is some symmetry. Until it takes this form, that is equation number 1, only then you can make the suitable substitution. There are some other methods also for different types of equations which are with variable coefficients but can be reduced to the linear form. There can be some more, but I have heard some students saying that this is mentioned in their syllabus. But remember, in case where it is mentioned linear differential equations with constant coefficients, and finally it is written that homogeneous linear differential equations with constant coefficients. If it is mentioned homogeneous, then you have to stop there. If it is not mentioned, if it is a variable coefficients reducible to linear differential, this constant coefficients, then I think this will also come there. But the students who are revising at this time for examination, they should only remember here the method of solution. That is how we substitute it, how we reduce this type of Legendre's linear differential equation with constant coefficients. They must remember the substitution is this a plus bx is equal to a raised power z. Sometimes in MCQ type, you may be given a Legendre differential equation of Legendre's form, and there you will be asked in MCQ type what is the method, this solution, suitable substitution, so that it gets reduced to the linear differential equation with constant coefficients. You may come across some questions in that case. In that case, you have a look. There is no problem. It is not a new one. It is not so difficult. It is same as what we did in previous lectures. I hope you have understood this. Now, will you do some examples on this so that you will come to know how to solve it? Do I share some examples? We will do some examples, this from engineering mathematics or some textbooks. Let us write some examples here. We will just write some examples. We will do some examples here. I will write here some applications for you. Just wait. Well, dear students, I have shared just one or two examples for your practice so that you can do the questions from your this text where you have the Legendre differential equations. You will do this way. Let me take first one. We have to solve the differential equation. Solve. It is 3x plus 2 square d2y dx square plus 3 times 3x plus 2 dy by dx minus 36y is equal to 3x square plus 4x plus 1. Let me solve this differential equation. I will name it first. You just look here. It is the linear factor square d2, second order derivative, then 3x plus 2, the same factor comes 1 dy by dx minus 36y. If it is here different, it is different, then you will say it is not the Legendre's differential equation. This is how we recognize the Legendre's differential equation. So equation number 1 is, first is Legendre's linear differential equation. How we go? We put substitution, put 3x plus 2 is equal to e raised power z, which implies that your z is log of 3x plus 2. This I need, and you will not go what we did in the article. This we derived there dy d2. You will not go like that. You will write now just here. Now our 3x plus 2y dy by dx is nothing. It is simply my this 3 b dy by d. It is 3 b is your this 3. This is dy, where d is d by dz. It was there b raised power 1 when it was ax plus b. And what is your 3x plus 2 square d2y dx square? Look here, it is 3 square b square in case of square here, 3 square. It is d into d minus 1 into y, where d is your this. If there would be cube, you don't have cube term here, 3x plus 2 cubed, you don't have. If it would be, then you would write 3x plus 2 cube d3y dx cube is 3 cube. It is d minus 1 into d minus 2y, but we don't have here. We will use this second and first here. I will name it second. This is third. Now using second and third, where in first, look here, 3x square d2y by dx square, it is this value. This you will write 3 square d into d minus 1y, where my d is d by dz. Come here, it is plus 3, okay. Then 3x plus 2 dy by dx, it is your 3 times dy, okay. Then minus 36y is equal to, well, we have to convert this here. This x value I have to find out here. You just look, it is very important because I have here 3x square. My substitution, I have put 3x plus 2 is equal to e raised power z. That means my x will be here e raised to power z minus 2 by 3. In this case, in this question, I put 3x plus 2 e raised power z. I want the value of x here. What is it now? It is e raised power z minus 2 by 3. I will use it on the right side here from equation number 1. Use here. What is this? 3x square. This comes out to be 3. What is your x now? It is e raised power z minus 2 by 3 whole square. It is x. Then plus 4 times, what is this? E raised power z minus 2 by 3. Then plus 1. Now my differential equation gets converted. It is now free of variable coefficients, and it involves y and z, where my z is given by this. Okay, let us solve it. Well, you have this, you can take this common. It is 9 d minus 1, 9 d minus 1, plus it is also 9 dy. y I will take common. It is 9d, it is minus 36 into y. Let me simplify this. This can be it is your e raised to power z minus 2 square by only 3, because 3 square gets cancelled. It is 4 times e raised to power z minus 2 by 3 plus 1. Yes, I will just simplify this. I can take a 9 here. This I don't need now. You see where we go. We can take 9 out. It is d square minus d. It is plus d square minus d. It is plus d. Taking 9, d square minus d. 9 is out. It is plus d. It is minus 4 y is equal to, take 3 LCM, and we can open it. E raised power 2z, it is plus 4 minus 2 e raised power 2z, a minus b whole square. This is plus 4 e raised power z minus 8, 4 e raised power z, 4 minus 8, and plus 3 here. Plus 3 will come here. Let us see what is now means. This is 9 times d square minus 4y is equal to, just look here, I can connect e raised power 2z square minus 4. It is not e raised power 2z here. It is e raised power z. It is e raised power z here. A square plus b square minus 2, 2s are 4, minus 4. It is minus 4 e raised power z only. E raised power 2z plus 4 minus 4 e raised power z plus 4 e raised power z. This goes plus 4 e raised power minus 4 e raised power. Well, this is your e raised power 2z minus 1 by 3. Do you follow? You get d square minus 1 minus 4 into y is now 1 by 27 into e raised power 2z minus 1. We have to solve this differential equation now. Now this differential equation, given differential equation 1 is reduced to this one, and what is this differential equation? It is free from variable coefficients. It is with constant coefficients. You can solve it. First you have to find out the it is auxiliary equation. What is auxiliary equation? Auxiliary equation is, it is d square minus 4 equal to 0. This gives you d square is equal to 4. This gives you d is plus minus 2. You are getting two values of this d. What is the complementary function? Two constants will get involved. C1 e raised power 1 value, say it is minus 2z, then plus C2 e raised power 2z, minus 2 and plus 2. This you get complementary function here. Then you have particular integral. How you find out particular integral? Okay, it is 1 by 27 e raised power 2z minus 1 by d square minus 4. It also gets divided into two parts. One part is 1 by 27 times e raised to power 2z by d square minus 4. Second part is 1 by 27, I will write outside, minus 1 by d square minus 4. Do you follow? Okay. I need complementary function. I will write for the time being this complementary function here. Complementary function for this question is c1 e raised power minus 2z plus c2 e raised power 2z. And other than this, I don't require anything. This is differential equation. I have done this. I have to solve this now. Now let us find the complementary particular integral. It is particular integral is 1 by 27. How we do for exponential? We have to replace d by this 2. It is 2 square. 4 minus 4, undefined. It is undefined here. How we follow? You remember the rule. We write here independent variable. What is that? Z. Then derivative of this. You see for this one, you write z independent variable e raised to power 2z. Z is out. Z has now no work to do. It goes out. Z e raised power derivative of this is by 2d. Do you remember? Because when we put here d, this 2 square becomes 4. 4 minus 4 is 0. When it is undefined, what you get here? You write the independent variable, that is this z. Then derivative of this with respect to d, it is simply 2d. You write this 2d. It is a derivative of only denominator. But in certain cases, it is 1 by another rule number 4th or 5th. There is something different. But here in this case, remember this, don't get confused. Here it is derivative of denominator only. Then for this part, it is minus. What I do here, I can write it e raised power 0z. I can also bring it in the exponential form. No problem. This comes out to be particular integral is 1 by 27. It is z by 2, 1 by d of e raised to power 2z, then minus, here I can replace, it is e raised power 0z. The coefficient of z is 0. It is 0 square minus 4. It is quite different. It is defined here. It is defined here. So my particular integral is 1 by 27. It is z by 2. It is integral of e raised to power 2z with respect to z, because reciprocal of d is 1 by d. It is integral of this. Then minus, it is again 1. It is 1 by minus 4. Okay. Now let us simplify this. It is particular integral is 1 by 27 out integral of e raised power 2z. It is e raised power 2z by 2. It is z e raised power 2z by 2 of this 2. It is plus 1 by 4. Well, this is particular integral is 1 by 27. You can take 4 here LCM. It is z e raised power 2z. This is here minus, yes. This was minus, yes, it is plus. Z e raised power 2z, z e raised power 2z, it is now plus 1 by 4. And this is your 1 upon 108. Just to look, 4 7s are 28, or then add together. Yes, it is z e raised power 2z plus 1. What is this? This is your particular integral. You have found particular integral also in this case. What is complete solution? Your complete solution will be now complete solution is the complete solution is y equal to complementary function plus particular integral. What is this y? This complementary function. This is your c1 e raised power minus 2z plus c2 e raised to power 2z, then plus 1 by 8, 1 by 101 by 8, 1 by 108. It is z e raised power 2z plus 1. Now see how we go. The value is here. I have to use this value. This value I have to use here. This 3x plus 2 is e raised power z, where I have z, this and this also gives z is simply log of 3x plus 2. Now write the solution. Write the solution. Y is c1 e raised to power z, e raised to power z here. When you write e raised power minus 2z, that will be according to this. It is your 3x plus 2 raised power minus 2. Similarly here, c2 3x plus 2 raised power 2. Raise here 2, you get 3x plus 2 raised power 2 raised power 2z. This is okay. Then plus 1 by 108. What is your z? You write z. Your z is again, it is log. Okay, this is your log of the value of z, log of 3x plus 2. Then e raised power 2z. What is e raised power 2z? It will be, you can write this first so that you may not get confused. We are multiplying with log. E raised power 2z. It is 3x plus 2 square. E raised power 2z, 3x plus 2 square. Then z. Z will be log of 3x plus 2. Then you have here plus 1. This, my dear, this is the complete solution of this problem. You have used the previous method of solution fully, but by a suitable substitution you could reduce this Legendre differential equation into one with the linear differential equation with constant coefficients. So in this way I have done this question for you. Let me take this also. You can even do yourself. Let me do it also, so that you are in a position to solve each and every question on Legendre's differential equation with variable values. Let us come here. This is the problem number 2. It is 1 plus x square d2y dx square plus 1 plus x dy by dx plus y is equal to sine of 2 times log of 1 plus x. This is the Legendre's differential equation here. Linear factor, square, second order, linear factor, linear, then y. Here also we don't have cube term. You can have sometimes cube term also. Now how we solve it? By Legendre's method. We put 1 plus x is equal to e raised power z, as we did in previous case. This implies our z will be log of 1 plus x. So that by this substitution, you should write here, by this substitution, what we get? We get 1 plus x dy by dx as 1 dy. What is this one? It is quotient of x. This is simply dy, where your d is d by dz, as we did in previous. Then you get here 1 plus x square d2y by dx square. It is this. You get this 1 square. Which 1 square? Coefficient of x. In the first case, in the theorem, In the second order result, the coefficient of x was there, a plus bx, it was b, and in second problem it was 3. Now it is 1 here. It is d into d minus 1 into y. Okay, using these in first. When we use it in first, where does our differential equation, which shape does it take? This will be replaced by this. It is d minus 1y. Okay, then plus this is your dy, and you have also plus y here. Plus y, yes, we have here plus y. Then is equal to sine of 2. It is log 1 plus x. What is our log? The log of 1 plus x is this. It is z. It is 2z. Therefore, you have this now, d square minus d plus 1. Y is sine of 2z. Therefore, our differential equation is, this differential equation is now reduced to this is d square plus 1 into y is equal to sine 2z. This is second equation. Now here you have to find out the complementary function, the particular integral, and so on. Let us see what is our auxiliary equation. It is d square plus 1 0. When you solve it, d square minus 1, d is plus minus iota, d is 0 plus minus iota. What is complementary function? Yes, in case of complex root, do you remember? E raised power alpha x, that is e raised to power 0x. Alpha is this. Then two constants, one with cos, one with sine. This is c1 cos of imaginary part, it is 1 cos of 1 into z. Then plus c2 sine of 1 into z. So I get complementary function here. It is 1. I get simply this c1 cos z plus c2 sine z. This is my complementary function. Now I shall go for the particular integral. What is particular integral? Particular integral is, it is sine 2z by d square plus 1. Do you remember? Sine ax by d square term is replaced by minus a square. I have only one d square here. So I will write particular integral is sine 2z, z का कोफिशिएंट 2, ये रिप्लेस होगा डी स्क्वायर से. इट इज माइनस डी स्क्वायर, दैट मीन्स माइनस 2 स्क्वायर. बी कॉशियस, माइनस तो आउट है, ये डी के बदले में ये 2 स्क्वायर बनता है. ये माइनस 2 का होल स्क्वायर नहीं, माइनस आउट है, प्लस 1. दिस इज इक्वल टू, आपने किए बहुत से प्रॉब्लम्स इसमें. इट इज माइनस 1/3 साइन ऑफ 2z. It is your particular integral. Particular integral comes out to be minus 1/3 sine of 2z. Therefore, what is complete solution? Complete solution is y equal to complementary function plus particular integral. Yes, this is what is your complementary function. It is c1 cos z plus c2 sine z, then minus 1/3 sine of 2z. And what is our z? Our z in the initial stage, I will again review your memory here. We have put this 1 plus x is equal to e raised power z, so that our z is nothing, it is log of 1 plus x. Now come here, this is solution is y equal to c1 cos of log z का value 1 plus x, the value of z, then plus c2 sine of z का value log of 1 plus x, this is the value of z, then minus 1/3 sine of 2 times z is again log of, it is log of 1 plus x. So you had only this is z here. We have replaced z by log of 1 plus x. Z is here log of 1 plus x. 2z, that is 2 times log of 1 plus x. This is the solution of this differential equation. It was a Legendre's differential equation. Now you have come to know how to solve the Legendre's differential equation. Those Legendre differential which are reducible to the linear differential equation with constant coefficients. I hope you have got this method also. Some students had asked for it, that Legendre's differential equation with variable coefficients, how we reduce it into the one with constant coefficients, and then solve by the previous method. I hope you have understood it, and you will do the rest of the questions yourself from your text, and you will also take into account the previous the lecture number 14 that we did. That is also the what is called this homogeneous linear differential equation. There also we could reduce that homogeneous linear differential equation with constant coefficients by a suitable substitution. When you will revise this lecture number 14 and 15, and you will really come to know that these one and this first method and second method for this homogeneous method, and for the Legendre it is one and the same, but a little bit difference is there. Thank you very much. See you next, and till then you take care. Thank you very much.